So hello and welcome back. So I hope that you get the solution by yourselves. You get the solution of this question by obviously by this question this solution by yourself. If you have not, I recommend you to watch the video, or just if you have find that out, also watch the video to check that to verify that your solution have matched with my solution or not. If I get somewhere wrong, so please tell me that please say me where I am wrong, or maybe let's go to the problem. So here we have the question, so let me do it. That so our first task, I have already told you, my first task is to find the eigenvalues of the matrix. So here we have the solution, so let me write down the solution. So my first task is to find the eigenvalues of this matrix. So what we have to do, we have to find the determinant of A minus lambda into I equals to 0, and we have to find the solution of this characteristic equation of the matrix A. So here we go. So if I write that down, so we get something like that. So we get 2 minus lambda 2 1 1 3 minus lambda 1, and we get from here 1 2 2 minus lambda, and determinant have to be equals to 0. So after the calculations, I will just now you can calculate. I think you can calculate the determinants. So after the calculations, I have already done it outside offline. So after the calculations, so we'll get the polynomial equation, something like that. So we get the polynomial equation lambda cube minus 7 lambda square plus 11 lambda minus 5 equals to 0. I have do it by myself, obviously by myself, in my different notebooks, not in online. So I just recommend you to do it, to solve it by yourself. You can obviously find that. First take this entry and then multiply with it, and then subtract with it. And I think you already know that how to find the determinant, and from the determinants you will get obviously this polynomial equation. So here we go. Now we're going to find the solution of this polynomial equations. So let me erase this and try to find the solution of this polynomial equation. So what we go here, from here, if you just there is no very special way to solve this type of equations. I have to use the basically a trial and error method. So if I put the value lambda equals to 1, what we get? So 1 cube is 1. So if I put 1 cube minus 7, we'll get plus 11 minus 5. So we get 6 and minus 6. So we get 0. So that's good that we have find that out, that lambda equals to 1 is a solution of this equation. So from there, what we're going to write this is in this form. So lambda minus 1, lambda minus 1, and lambda minus 1, which is equals to 0. So first we have lambda cube, so lambda square, we get lambda cube minus lambda square. So we have minus 7 lambda square, so we need to have minus 6 lambda square extra. So we have to multiply minus 6 lambda plus 6 lambda. So we need extra 5 lambda, so we have to add 5 lambda. So here we get 5 lambda minus 5 equals to 0. That's great. So we get the lambda minus 1 into lambda square minus 6 lambda plus 5 equals to 0. So either we get the lambda value, eigenvalue. So either the solution is either lambda equals to 1 or lambda square minus 6 lambda plus 5 equals to 0. So next do it with this polynomial equation. So I will going to solve this polynomial equations. So one eigenvalue, already we achieve one eigenvalue. So let's write that down. So we get one eigenvalue which is lambda equals to 1. So let me write that down. So we get lambda equals to 1. This is one of our eigenvalue, and next what we're going to do is solve the solution. So here we have lambda square minus 6 lambda plus 5 equals to 0. That's an easy equation, so we can solve it. Obviously, minus 5 lambda minus lambda plus 5 equals to 0. So from there we get lambda minus 5, and obviously we get lambda minus 1 equals to 0. So from there obviously we get the two solution of lambda. One is again 1 and another is 5. So we have eigenvalues. We have basically two different eigenvalue, but we have more. In total we have 3 eigenvalue. So we have two different eigenvalue. One is lambda, another is 5. So eigenvalues of the matrix A are, so let me write down the 1 2 times. Do not forget to write 1 2 times. So eigenvalues, so first step is clear. So eigenvalues of A are 3 eigenvalue 1, 1, 5. So we get 3 eigenvalue 1, 1, 5. So the first step is done. First step we have done the first step. So next is we have to find the corresponding eigenvector. So with respect to the eigenvalue lambda equals to 1, we're going to have the eigenvectors, and we'll also have to find the eigenvectors corresponding to the lambda, corresponding to the eigenvalue lambda 5. So let's do it. So try to find the eigenvectors with respect to the eigenvalue 1. So here we go. So first task is to find eigenvector. So eigenvector corresponding to the eigenvalue corresponding to the eigenvalue lambda equals to 1. So to find eigenvectors, so not like the vector, eigenvectors maybe, so we have to find the eigenvalue of lambda equals to 1. So what we know from the definition of eigenvalue and eigenvector, so that we have a matrix A, so corresponding eigenvalue is the matrix X, so that if I multiply A with the X, so instead of X let me write the something different, otherwise you may get confused. So instead of X we just write something different. So for example I just take the eigenvalue. So let me write down the eigenvectors, corresponding eigenvectors. Suppose the corresponding eigenvectors is y. So corresponding eigenvectors is y equals to. So what the eigenvector means, if we multiply the vector y with the matrix A, then we get vectors which is parallel to the vector y, but maybe with different magnitude. But here we get the same magnitude because lambda is 1, so 1 into y. So formula was ay equals to lambda y. So y is the corresponding eigenvalues. So ay is lambda y eigenvector. So lambda 1 is the eigenvalue. So we put the value of lambda. So ay equals to lambda y. So now put the value. So I think I have problem with space. So let me do it. I have no choice. So here we go. So we have a matrix. So put the matrix is 2 2 1 and 1 3 1 1 2 2, and suppose the corresponding eigenvectors is y1 y2 y3. Obviously this is a 3 by 1 vectors because we are talking about vector in 3 dimensions in R3. So because we have 3 by 3 matrix, so we need a vector 3 by 1 and equals to y1, 1 into y1, so y1, y2, y3. So from there what we get, so if I multiply the matrix, so what we have to do, we have to multiply this row with this column. So after that we get 2 lambda 1 plus 2 lambda 2 plus y3 and y1 plus 3 y2 plus 1 y3, and third one is y1 plus 2 y2 plus 2 y3, which is equals to our eigenvectors y1, y2, y3. So from there, now these vectors and these vectors are equal, so each component, so all may be called, each entity have to be equal. So this entity have to be equals with this entity, this entity have to be equals with this entity, and this entity have to be equals with this entity. So from there what we get, so if I write that down, so first let me erase this part and then write that down. So I think I can now erase the question also. I hope you have already remembered the question. So here we have 2 1 1. I think we can remember the matrix, so we can erase this matrix. So from there what we get from this equation, so let me write them down first. So from there we get the matrix, so we get 2y1 plus 2y2 plus y3 equals to y1. So this implies, if I take y1 in this side, we get y1 plus 2y2 plus y3 equal to 0. So this is our equation 1. So next, from this part, this have to be equals to this. So from there what we get, so we get y1 plus 3 y2 plus y3 equals to y2. From there we get y1 plus 2y2 plus y3 equals to 0. Now let me write that equation 2. Now you can see clearly that equation 1 and equation 2 are same, so we do not get a different equation. So let's check from the third entity what we get. So third entity is over here and here is this. So from third entity we get y1 plus 2y2 plus 2y3, which is equals to y3. From there we get y1 plus 2y2 plus y3, which is equals to 0. So from there we get basically the equation 3. Now you can see that equation 1, equation 2 and equation 3 all are same. So from all that equations we get only one equation. So because we get one equation and 3 are unknown, so one equation, 3 unknown, so obviously how to solve this part. So let me do it. So first let me erase this part and next do it that part. So one equation, 3 unknown. So from there we get, so let me change the thickness of the color. So we get y1 plus 2y2 plus y3 equals to 0. So what you can now do, from there we can write y1 equals to minus 2y2 minus y3. So now we have the vector y is basically y1 y2 y3. So we have the vector y1 y2 and y3. What we going to do, we're going to put the value of y1. So from there if I put the value of y1, we get 2y2 minus y3 and we get y2 and y3. So y, the vector y can be written in this way. So if I take the common y2, So you can write this vector in this way. I think you can find it by yourself. 1 minus 2 1 0 plus, you can see that we can write y3, and from there we get the vector minus 1 0 1. So we get basically, so different value of, so y vector, the vector y is can be written in this form. So different, if I put different value of y2 and y2 and y3, we get different y. So there are infinitely many solution, or infinitely many y will get. So there are infinitely many eigenvectors corresponding to the lambda equals to 1, but not of all of them are basically going to be linearly independent. But you can, I going to see that these two vectors are linearly independent to each other. You can see that easily. Or the vector from y, what we're going to do, we put y2 equals to 0. So eigen corresponding to eigen value lambda equals to 1, we get different eigenvectors. So for different value of y2 and y3, we get different solution. So for corresponding to lambda equals to 1, we get different eigenvectors. We get infinitely many different eigenvectors, but not all of them are linearly independent. So I think, so from there, if I put, so two particular eigenvectors lambda equals to 1 are, so two particular eigenvector corresponding to lambda equals to 1 are, so let me so two eigenvectors, so two particular eigenvectors to two vectors corresponding to lambda equals to 1, corresponding to lambda equals to 1 are, so what we're going to do, we put y2 equals to 0, so y2 equals to y3 equals to 1. So by putting y2 equals to 0, and y3 equals to 1, so different value of y2 and y3, we get different eigenvector. So I just put particular value y2 equals to 0 and y3 equals to 1. What we going to have, we have the eigenvectors minus 1 0 1. So we get the eigenvectors minus 1 0 1, and another one we're going to do, we're going to put y2 equals to 1 and y3 equals to 0. So you may ask why I take these two are eigenvectors as eigenvectors, because you can see that all the solution are basically the linear combination of this vector and this vector, because here we have a scalar and vector plus scalar and vectors. So all the solution, all eigenvectors y can be written as a combination of these two vectors. So that's why I am particularly taking these two vectors as our particular eigenvectors. So from there I can hope that these two vectors will be linearly independent. So that's why I am taking only these two eigenvectors. You may take different eigenvectors, but they may not be going to equals to linearly independent to each other. So that's why, because we can write each and every solutions as a combination of these two vectors. So that's our maturity says that I can take these two vectors as our eigenvector, and from there we can check they are linearly independent or not. So what we're going to do, we just first erase this part. So remember that we have get eigenvector minus 2 1 and 0. So corresponding to y2 is 1 and y3 is 0, we get minus 2 1 0. So we get eigenvectors minus 2 1 0. So we take these two eigenvector. So now stop over here. So what we're going to do, we're going to check these two eigenvectors are linearly independent to each other or not. So if we write C1 into minus 1 0 1 plus C2 into minus 2 1 0, which is equals to 0 0 0. So 0 0 0. So what we get from there, we get basically minus C1 minus 2C2 and C2 and C3 is equals to 0 0 0. So from there we can easily find that C2 must be equals to 0, C3 must be equals to 0. So C2 is 0 and C3 is 0. Since both C2 and C3, sorry, here actually I have made a problem. So here we must have C1. So instead of C3 have to be C1. So C2 is 0 and C1 is 0. So because both of them are 0, so these two vectors are linearly independent to each other. So these two vectors are linearly independent to each other. So we already get two linearly independent eigenvectors corresponding to a matrix A, obviously corresponding to the eigenvalues lambda equals to 1. So for lambda equals to 1, we get two different eigenvectors. So let me find the eigenvectors corresponding to lambda equals to 5. So before all that, let me erase this first and write down the eigenvectors, two linearly independent eigenvectors. So corresponding to lambda equals to 1, we get two different eigenvectors. So for lambda equals to 1, what we get eigenvectors minus 2 1 0, and we get another eigenvector. So this is not I, just is I am taking. So if you do not confused with that, just I made a full stop and comma. So just let me write the comma. So here we have another one, minus 1 0 1. So they are our two linearly independent eigenvectors corresponding to lambda equals to 1 of the matrix A. Now going to find the eigenvectors corresponding to the lambda equals to 5 or corresponding to the eigenvalue 5. So let me write that down. So here we go. So for lambda corresponding to lambda, for lambda equals to 5, we're going to find the eigenvectors. So what we're going to do first, obviously, right? So here we get A into some vector Z have to be equals to 5 into Z. Z is our eigenvectors and lambda is our and 5 is our eigenvalue. Lambda is 5 over here. So we're going to find the Z. So A is, let me write down quickly what is A. So A is 2 2 1. So let me write that down. So A is our 2 2 1, and second row is 1 3 1, and third row is 1 2 2. And suppose the matrix Z or the vector Z is a 3 by 1 vectors with entries Z1 Z2 Z3. Suppose we have this entry which is equals to 5 Z1, so which is equals to 5 Z1 5 Z2 5 Z3, because if we multiply 5 with Z, you get 5 Z1 5 Z2 5 Z3. So from there we get, so from there if I multiply this matrix with this matrix, so we get a 3 by 1 matrix with 2 Z1 plus 2 Z2 plus Z3, and from here Z1 plus 3 Z2 plus Z3, and here we have Z1 plus 2 Z2 plus 2 Z3. I obviously recommend you do it by yourself. Do not copy my lecture video, and I just obviously recommend you to do it by yourselves. From there you will have some practice and you may get a good results from that in future. So from there, so because we have 3 by 1 matrix here, we also have a 3 by 1 matrix. So this entry have to be, so each entry, this entry have to be equals to this entry, this entry have to equals to this entry, this entry have to be equals to this entry. So from there if we write that down, so from there we get, so first equation will be, So let me increase the thickness. So from there we get 2z1 plus 2z2 plus z3 equals to 5z1. So from there we get minus 3z1 plus 2z2 plus z3 equals to 0. Now this is our equation 1. From the second entry what we get, so from second entry we get z1 plus 3z2 plus z3 which is equals to 5z2. From there we get z1 minus 2z2 plus z3 who equals to 0. So we get a different equation. That's good. So and from third one we get z1. So from third entry is here, so z1 plus 2z2 plus 2z3 which is equals to 5z3. So from there we get z1 plus 2z2 minus 3z3 which is equals to 0, and we get equation 3. So we get three different equations. So what we're gonna do, we're going to from 1 and 2 we're going to find the value of z1, z2, z3, and we put the value of z1, z2, z3 in 3 and check what will going to happen. So first let me erase this part, and from 1 and 2 what we get. So from 1 and 2, so let me erase this part, and from z1 and z2 what we get. So let me write down z1 by this, z2 by something, z3 we're going to have. So we are using equation 1 and equation 2. So I'm sorry, I have battery already out of power. So from z1 and z2 what we get, from z1 and z2 I have to end this video. I think I have to end this video over here, and I have to continue the video in the next part. So I'm sorry, I have to stop this video over here, otherwise I cannot get the full video. So thank you.